Welcome to CarbonCraft X, where we specialise in testing carbon fibre bike frames using the latest tech. Today, we'll be focusing on the top tube of a carbon bike frame, subjecting it to a series of tests to detect damage that's invisible to the naked eye. Using precision tools and advanced methods, we'll pinpoint hidden delaminations, cracks and fractures before they become a problem.
Hi, I'm Lloyd, and today we're going to demonstrate how we test the carbon fibre top tube of a bike frame for damage that isn't immediately visible. We'll be using a 450 gram or 16 ounce hammer and progressively dropping it from different heights to test the structural integrity of the frame. As the test progresses, we'll be using cutting-edge technology to spot damage before it becomes apparent on the surface. This is critical because it means that we're going to be able to prove that there is damage to the underlying carbon fibre structure, while you would not normally be able to find that by looking at it or feeling even the surface. So let's get into it. Before we begin, let's set the stage. This bike frame has already been involved in a strong head-on collision and is completely irreparable. In the collision, the fork proved to be exceptionally strong. So strong, in fact, that it withstood all of the force of the crash and transferred it into the bottom of the head tube, completely destroying it. Miraculously, the rider walked away without a scratch. The extra good news is the rest of the frame is perfect for testing. Notice here the head tube's damage. It's completely compromised after the crash. Importantly, the top tube is still intact, and we've confirmed this through inspections that it's in solid condition for our tests, with one exception being this small delamination here, which we detected using ultrasound. Now, we'll put the top tube to the test and really drop the hammer. Okay, here's the setup. We'll be dropping the hammer from predetermined heights onto the top tube, which is resting on the surface here. We have a simple tape measure. We're not aiming for pure, perfect scientific results. We're aiming for a general feel for how it would be at home or out on the road or out on the trails. So what we're trying to replicate is what happens if you drop your bike or have a crash and it hits a rock, it hits the sidewalk or another car or a post. It's an indication of what's going to happen. At the end of this, we're also going to be able to tell you exactly how much force, plus or minus, in terms of newtons, that this exerted on the carbon fibre frame. In addition to the camera setup, we have our borescope, which is currently positioned inside the frame. And we're also going to have a digital microscope to check it. After each drop, we're going to be running a full ultrasound scan on the area that was impacted, in addition to active thermography. Let's get it going. Number one. Whew. This is 40 centimeters, double the height from the last drop. Let's give it a go. Doesn't have to be perfect. It's going to be pretty close though. Okay, 3, 2, 1, and whew. Yikes. Could be an expensive episode. All right, test number 3. 60 centimeters, triple the height. Now we're getting up to the height of the actual top tube when the bike is at rest for the smaller frames. It'll be interesting to go beyond that. I hope it doesn't take out the camera, because this is a lot of force. All right, 60 centimeters and, ooh, yep. Okay, we definitely have some visible damage. Drop number 4. This is getting really high. This is 80 centimeters, so you'll find the vast majority of bikes, the top tube is within this range. So this is really going to be, around the max damage you can do, but that won't be the last test. This is getting genuinely scary because it bounced about 2 feet from the last one, but let's try it out. And dropping in 3, 2, 1. Woo! Okay. That one, definitely we have some damage to the paint on the outside, but it looks superficial. We'll determine what happened with the ultrasound. Fun test number 5. We're going to smash this as hard as we can, and then we're going to run the tests across all of the different areas to see what damage has happened. We've got our borescope running, we have our slow-mo, and we have the main camera. Let's go. Okay, 1, 2, 3. Ooh, I see visible damage. I heard a lot of rattling. Let's see what we find.
Moving to number 1, to look at the microscope, we can see here there's no additional damage other than the scratches that were previously present on the paintwork. Magnifying in a bit further, we can still see that there's nothing other than some superficial scratches. Looking at number 2 after the drop, we don't see too much issue. Zooming in further, we then have a look at the paint and we're still not seeing any major issues with the surface. After drop 3, we can see here there's clear chips in the paintwork. There are also some wrinkles in the paint as well on the white section, and down below, if you look carefully, you'll see some fractures in the black section. Zooming in further confirms the paint chips, of course, and we can see that there's some separation and wrinkling or slight overlapping with the paintwork that was not there previously. Number 4 here, you can see that there's a slight circular pattern of cracks, very fine lines. Magnifying further, you can see that there's clear stress fractures within the paint job itself. We'll see how that translates underneath. And there's even a small paint chip just on the edge of the white and black area. The carbon there is exposed. We'll have a look. There appears to be a very fine crack in the carbon itself. We'll have a look with the ultrasound soon. Number 5, the smash test. There's very clear paint chip up in the white section, and there's also very clear cracks in the paintwork. Looking at the higher magnification, there's very clear stress fractures along the entire paintwork. This would be around where the hammer struck, of course. And then looking at the black section, you can also see that that stress fracture in the paintwork is also gone well into that black area. And there's also a small paint chip here in the white area. Again, stress fractures in the paintwork are clear and visible throughout the entire series of images. Here is the active thermography after the tests. Unfortunately, it was not able to reveal any further underlying damage other than the paint chips that were already visible.
So I've done the preliminary check of target 1, where we dropped the hammer from only 20 centimeters. I'm applying the couplant now, and we're going to do the ultrasound test. Now, I think I've found a crack, quite surprisingly so, but also not surprising on the basis that we did drop a hammer and a lot of the force would have been likely concentrated in one small section. So what you see on the screen now is the transducer from our ultrasonic machine, and we're going to just check a few basics around here. So if you look at the top left of your screen, you'll see that we're measuring approximately 1.27 millimeters in thickness, and it's very consistent as I move it across the surface here. And you get small variations, and that is common. These tubes you normally have different thickness as you progress along, And that different thickness is due to maybe some small wrinkling, maybe a bit of extra plastic left over from the bladder being pulled out, depending on the manufacturing. Many factors. But it's well within tolerance, right? So if we start exploring around here, we get a different thickness there, but it's still within, 100th or 200ths of a millimeter. However, if we do come here, I've noted that there is a very clear drop. So if I just rock the transducer ever so slightly, we get half the thickness that we're expecting, which tells me there's either a crack or a delamination. I would suspect a very small delamination. And it's in this area around where the decal is. Now, is this as a result of the decal? I would say no, because if I follow along this line, it goes back to normal thickness, and then I progress back towards it, it drops again. So I think we've got a very clear delamination, or a crack in this case, and it progresses all the way out to approximately 3 or 4 millimeters past the end of that decal. So see that there? If I move back to the right hand side, suddenly we get our measuring again. If I rock it downwards, it goes away. And if I rock back up, we see that we get the larger measurement again. So this for me is a very thin delamination, likely a crack. And it's approximately $5 mil more. It's about a centimeter. Yep. So I'll mark this out, and when we cross-section this, we'll see what we find. But definitely a flaw in the material that you would not want, and 100% not visible to the human eye. And you'll be able to see that in the digital microscope that we used before. Let's just clean this one up. All right, and just recalling that the delamination or crack itself sits here. So we're going to mark that. And we can double check it later on, but my feeling is it runs from about here all the way to about there, which would be consistent with the hammer hitting it likely in one point. Let's move on. Okay, number 2, I've cleared this area. The main reason being, I know from the slow-mo footage that it dropped here, and I remember when I dropped it, I was a little inaccurate. C'est la vie, but let's keep having a look. So there's a very obvious paint chip here, which I know wasn't there when I first dropped it. So clearly some kind of damage. Let's see if it's actually deeper. Okay, so we've got a rough thickness here of about 1.5. And as we go across, so we see a very clear delineation where it hit. Let's have a look in the area surrounding it. Yeah, so there we go. We have a very drastic drop in depth of about 50%, and I'm expecting this to continue on a little bit further. Yes, it's continuing on. This is a clear crack or delamination, and it's stopping right about there. Yep. So that's interesting. Let's rock it a little bit. Yeah, so we've got our measurement just there. That's where it stops. So it's about a centimeter again in width, which makes sense. That's consistent with the damage in the first drop. And let's just pull it back a bit. Yeah, we've got same depth. And it continues up to what appears to be the impact point. Oops, I'm moving things around. But I think we've got a pretty clear case where it's going to need a cross section, because just outside of this area you've got a nice continuous thickness, which doesn't vary that much across the tube. It's very reliable. As mentioned, these tubes are laid up by hand, so there is some variation in it. And on the other side, get some couplant under there. Yeah, we have a similar measurement. So I would say yes, there's a definite case for damage here. And it is right along this line from the chip. And it's about, yeah, it's about 1 centimeter out from the chip. It is not very wide, so it stops when I roll the transducer that way, and it stops again when I roll the transducer this way. So I'd say this is a definite crack based on the style of the damage that we're seeing, and on the other side of this is actually perfectly fine. So interestingly, the crack is directly between here and about 1 centimeter over there. So that is what we're going to mark. So we've applied the couplant. We're going to check out number 3. I think a safe area away from these significant paint chips is good to start, and we get a consistent measurement, okay? And if we go along, we see that it varies a little bit, but it's within normal manufacturing tolerances, right? So I think that's nice and consistent. Let's check around this area. So I've found it's a hive of activity in terms of faults. So this would be very interesting to cross-section. We're going to see everything is my guess. But we don't see, so suddenly we go from very little to, I'd say we've got a significant amount of cracking that's propagated out from that impact point. It's very clear. Slightly over here, we've got delaminations, and back to normal there. And then interestingly down here, I believe, we also have, yeah, quite a lot of cracking and delaminations. The readings are not what you'd expect. If I pop it down here where, say, the 3 is, then we get a consistent measurement. Just need to hold it steady. And we get a consistent measurement of about 0.83 mil. Okay, so that's nice and consistent. But then you move up and it halves, and it goes back to crazy town. So these measurements here show that there's been an extreme impact here, and I would suggest this part was compressed. It's going to be delaminated, and then around here is likely going to be a lot of fractures and cracking, and you see that in the results. So there's all sorts of jumping around, there's signal loss. It's, in my opinion, it's going to be a complete mess inside this part of it. If I move slightly over here, we get consistent results again. If I move it along, it suddenly drops and then it goes to nothing. So this is going to be a combination of delaminations, cracks in the matrix, probably paint has also debonded from the outer carbon layer. And again, here you've got about half the thickness that you would have slightly further over here. There we go, or even less than half the thickness. So that's an extremely deep crack and delamination within the carbon structure itself. This is going to be very interesting to cross-section, and we're going to see all sorts of damage, so I can't wait to unveil that one. This is just going to be a great big circle, this whole section here. Fantastic for cross-sectioning. Okay, so number 4 really doesn't look that bad, but based on numbers 1 through to 3, we know it's going to be terrible. You can see clearly we have some disbonding of the paint from the frame, some wrinkling over here, so we know, and there's what looks like a significant force that's come through here. This is going to be ugly, guaranteed. Let's put some couplant on, just 1 drop, because that's all we need. It's actually way too much couplant, but it doesn't adversely impact our results. Okay, so let's get a normal reading over here first. Wow, I think we need to go wider. Yeah, oh wow. This is gonna be nasty. Okay, so we get the normal reading we've been expecting from the rest of the tube, okay? And we get the normal reading about here. I go in a bit and it's already showing signs of delamination. Now that is not a surprise, given the amount of force. This is dropped from 80 centimeters, which is well within the region of a fall with your top tube hitting the ground from basically full vertical. And as we can see here, just make sure we've got the right couplant to mount. Yeah, so there's a clear delamination, maybe a crack. No, that's a delamination, it's too big for a crack. Yep, so that's nasty, and we can follow this, yeah, all the way in, and it's going through several layers because you can see the depth is changing. And then, yeah, so this is where the impact point would have been roughly, and that's consistent. So I believe this whole section here has been, wow, totally ruined. Interestingly, it stops around here. So the delamination has moved to the right-hand side of the screen, and it stops. Oh, where's it gone? No, it doesn't stop. No, it was just an optimistic measurement there. Yeah, so it's a train wreck. This whole thing is a train wreck. Oh, that's an interesting reading. No, so we're getting good readings here. Oh, some bad readings here. Now, I'm not surprised given that the force was pretty extreme. But yeah, we have a completely wrecked top tube. Yeah, so there's fractures that are permeating out from that impact point and they go everywhere. So this is a great big circle in terms of damage. I'm quite keen to take a look and see how it is. Yeah, so you just go straight from healthy to unhealthy. That's amazing. So yeah, we've got a lot of investigation to do on this one. We'll cross-section this and I'm sure we're going to get some interesting results. Okay. We should do a tap test. We totally should do a tap test, but that is another episode, my friends. All right, last but not least, this was the bonus smash. Let's put the couplant on. Now there's two obvious areas, here and here, where there was some paint chipping, which is fine, but I'm expecting this to be by far a disaster. So at least that bit's consistent and able to read. Oh, but it's delaminated all the way. We really ruined this. This carbon frame's had a bad day. Not the first bad day it's had. But yeah, if I push really hard and force the layers together a little bit, I can get a measurement. But we are struggling to get something out of this. So yeah, yeah, the bonus one with medium strength on the hammer is, yeah, okay, so here's a good initial reading. Okay, it's very clear. Initial reading about there. That's the normal thickness you'd expect. It's what it's been across the entire top tube. You roll it up a little bit and it drops and it drops, and the closer you get to the impact point, we continue to find delaminations and cracks, and then we promptly lose all signal because it's such a complete mess in the structure. It's near impossible to measure. So this is a disaster. It's time to cut through the tube. I hate doing this. No carbon frame should ever go out this way, but this is for research. Let's start. Okay, time for cut number 2. It's going to be at the edge of the tube here so that we have one continuous top tube
previous cut is already complete. Nothing left to do but to do it. Last. There we go. Okay, so we have our carbon fiber top tube here. We're now able to look at cross-sectioning it in positions 1, 2, 3, 4, and 5. This will give us the ability to have a look at the actual carbon fiber itself and see just how bad those cracks, fractures, flaws are. And we'll have a look at that with the digital microscope. Before that, let's clean the mess up and we can start. So we have the top tube here and we have our oversized saw blade guide. And we're going to be taking our carbon fiber blade and cutting in through here. Now, I've placed it just so we can cut through that one crack that I believe I found in the first one. But before we do, we're going to have a closer look down at this so I can confirm that we're going to hit the right spot. Okay, so here we have the saw guide and the top tube. And there's a small white mark that I'm pointing at right now, as you can see. So next we're going to place the carbon blade into the guide to make sure it lines up with the middle of that mark. And perfect. Time to cut. We want this to be smooth so that we can get a good cross section. If it's not smooth enough, we'll sand it. And we're through. All right, so we have our cross section in here and here. We can examine both and we'll see just how it looks. There's that one. All right, back on the shelf. We're just going to keep cutting all of the different segments in the spots directly through where we found faults, and then we're going to check them all with the digital microscope. So let's do it. One down. Whew. Perfect. And continue. All right, number 3. Number 4 is where we had a lot of damage. So pretty much anywhere in that sphere of destruction is good. Gets faster every time. Secure. And the last piece. We have our cross sections. We will be sanding these down. Here are the cross section tubes. We're going to take a look inside of each one of these in just a second, and then we're going to sand the cross-sectional area here and use the digital microscope to see what flaws we can absolutely verify that were detected by the ultrasound. Let's do it. Here are the segments that we've managed to cross-cut and get here for you. Now this is the number 1. Interestingly, on the inside, you can actually see here a faint line. Now that line is the bonding point between the two halves of the frame. There is a similar line on the other side, just near here. A bit hard to get the focus to work. So yeah, that's interesting. We'll see if that line or the crack that we detected, which is right there. Oop, there we go, right there. We'll see if that is what we actually upset or managed to break the bonds on when we hit it with the hammer. Likewise, you do have section 2, and if we get the angle just right with some light, there we go, my hand reflects light, that's nice. You can see on the inside, and this is very typical
of almost every carbon bike out there. It's very rare to get a smooth inside, but you can see there's very, very small bumps and imperfections in the carbon. Now that's very typical, almost impossible to remove from manufacturing, but it is possible on very high end, but this is extremely normal and it doesn't degrade the integrity at all. And then just take a look at a couple more of these. So you do have this guy. Here is a good example of the, you can see that in the background of the bond between the two halves. And then similarly on the other side. Yeah, a bit hard to get the right angle on that one, but we'll review those later. Oh, now this one's interesting. Not sure if you can see all of that, but there is significant I would say not wrinkles, but warps on the inside of that. So quite significant, pronounced, easy to see. That's interesting. Again, doesn't degrade the integrity. I don't see any outright wrinkles, so that's no problem. And the final piece. Yeah, and you can see a similar thing. There's plenty of, again, a bit of overlap on the different layers of the carbon during layup. Maybe this was caused by the bladder as well. That's entirely possible. So there may have been wrinkles in the bladder when it was inflated, or small overlaps there. Again, all of these are very, very normal, and when I'm measuring with the ultrasound, for example, you will see a thickness change. Now, thicker is good, thicker is heavier, thicker is stronger, normally. We don't necessarily want thicker because it may not be needed, and more importantly, it's obviously going to be heavier, so performance is the key. But thicker will not be a bad thing for safety. All right, let's get these sanded and under the microscope. Now we're going to try to grind down or perfect the surface of the cross section of each of these pieces of carbon. We've got a number of special grinding discs. I'll show you those right now. Okay, so these are the grinding discs. These guys are diamond tipped or diamond impregnated grinding discs. Here we have number one. So this is the first cross section. In this cross section, we detected what we thought was a crack about 50% of the way through the material. So there's the mark, and I believe I see a small crack. Let's just make sure we point it out. So the small crack I believe I see is right here. It's not a crack, it's a fracture, or I'd say that's a fracture, it's not a delamination. Now, it's very small, it was about halfway through, which is what we detected, and it's exactly where we detected it. Let's see if we can compress it a little bit using this small vise. So there's the crack we detected under some more compression, and as per the ultrasound, it was roughly 50% of the way through the material or the carbon. If we keep applying pressure, I'm sure we'll see that propagate further. Let's do a little bit more. And twist. Okay, let's have a look at that now. Yeah, so that fracture is very obvious.
and it's not a major concern. It is a potential future concern. As it spreads, it is very small. You know, to give you an idea of scale, this is the hook that I'm using just to point it out. There it is. And the scale of the hook compared to my finger as a close-up, I mean, I hope that gives you an understanding of the resolution that the ultrasound can detect. It is extremely detailed. So this is the other half of number 1. So as you can see, just there. And we want to have a look under the microscope. So this was a little bit chipped, but the chip is not what we're looking for. We are looking for the crack that we detected. So there's the chip. Okay. Now, can we see the crack? No, we can't. That's interesting. Let's put it under some pressure. Okay, so we have a little bit of pressure on it. And I believe, yep, there it is. So very, very quickly, with a small amount of pressure, you can see that that crack is now visible along here in the same position. So that was what we detected and continued along. Let's open it up a little bit more. One more half twist. Oh yeah, that's gonna open. Whoa, okay, yep. Yep. So this is not a normal scenario. Obviously you wouldn't have the carbon tube under this much pressure, but it's a really brilliant example of only 20 centimeters drop has produced a crack in the material. So you know what? I'm gonna get the scale out. Okay, so for clarity, this is the crack that we discovered in scan 1, and it's 2 millimeters in width. That is all. Here we have number 2. This is the first half of the cross section that we took, and right about there, it's very difficult to see, but that is where the mark was made. That's where I detected a small delamination or fracture. Let's have a look under the microscope. So here is the mark, and interestingly, I can't see any major issue. There's obviously an issue down here in what looks like the last layer of carbon fiber, but that's not what we detected. So let's put it under some pressure and see what we find. With a bit of pressure, we've now revealed exactly what the ultrasound had detected. And again, right here is where we said it was. And what you can see here is a very clear fracture that's going through. Now this has to be going through some layers of carbon fiber. It's about 1 millimeter, which is what we were able to detect. Again, this is a very minor fracture within the carbon. Is it going to be a major issue for now? No. Would it be something that we monitor over time? Absolutely yes. The chances of this propagating are pretty high, especially given that you can see down here, it has continued to propagate from here. So most likely this was caused also by the hammer drop, and it's propagated up through 1 or 2 layers of carbon and is now following along the resin matrix. Let's look at the other half of number 2. All right, so here's the other half of numero 2, and that is where the flaw was detected. Looking at it under here, interestingly, you can see, it has to sharpen the focus a little bit. You can see here now that there has been some actual compression damage to the carbon. So you see there's a gap right there between the paint layer and the carbon. That is a very classic case of compression damage from where the hammer hit.
But interestingly, I can't see any fracture, but I marked it as going deeper. So let's apply some pressure and see what it shows us. Okay, we have some pressure. So here we have a very clear delamination or a crack, as you can see here. And again, this is where I marked it with the ultrasound, and we can see that that delamination or crack has formed there. So it's equal on both sides. You can see you've got the slight delamination or debonding of the paint, and then you have the crack internally with the carbon fiber. Again, this is something you simply cannot see from the outside. The paint layer itself is in good condition. So looking again at the paint layer over here, so that's where it was. You can see that visually there's nothing wrong with it, but there is a crack. Now we're talking 40 centimeters. We're now going to look at number 3, this side, and see if we can find any cracks or delaminations, remembering that it occurred in this marked area here, within this circle that I marked. So let's have a look at that cross section under the microscope. Okay, so it doesn't take us very long to see there's some clear fractures and delaminations within the material. And these are obviously running not just through the matrix or the resin itself in between layers, it's running through layers here. This little part here, this is simply some excess resin, I would say left over by the bladder that was previously inserted during the manufacturing process. That is not the problem. Now, if you look at the surface itself, the surface has the paint chip, which you can see there. I'll bring it up to the main camera. So you've got the paint chip just here, and it doesn't look all that bad. It really doesn't look all that bad. But we can see clearly it is a major problem. Now, this is going to be very interesting when I squeeze it. We'll just pop the device on. Device is on. Woo, that looks ugly. So you can see there's been a massive failure of multiple layers, multiple fractures, and they go deep and far in the material, and they terminate. Interestingly, notice the white marking. That's where I marked. So the white marking is where I marked the end, right here, of the fractures and cracks, and that's exactly where it ends. And so this is going to continue deep, deep, deep within the material to where I finished marking it out. But yeah, this one you can see deep into its structure. So that is scary, because that's only 60 centimeters. And it has caused what I would consider a catastrophic failure. This would not hold up under pressure. You can imagine this tiny little vise has next to no strength in it. I needed one single turn. So imagine hitting a pothole on your bike. So let's move to the other side of number 3. So here we have the other side of number 3. And again, it's just a small paint chip. It doesn't look all that bad. Internally, it looks all right. Doesn't seem to be a lot of damage, but let's have a look. Ooh, okay. So we have very clear destruction. So the main impact is here, and you can see that the shattering effect has impacted all the way to over here. So you've got multiple fractures, delaminations, matrix cracks. I detected that it ended about here, where the metal spike is, and that's exactly where it finishes. And I'm going to apply a little bit of pressure again. Okay, we've got a tiny bit of pressure. Wow. Wow, that's pretty serious fracturing within the material. It's obviously going to be at a fraction of its strength, and again, this will guaranteed fail over time. Could be the next pothole, could be the next speed hump. Let's move on to number 4. Number 4 is the one we marked. Now, we said we had a very significant damage area, so being all of this area here. This will be interesting to see just how deep that goes. But again, the paint looks fine. It doesn't look like there's a major problem. Let's see what we can find. Straight into the microscope, and I don't see, I do see a fracture just there, but it looks very deep. I'm wondering, so obviously the fracture for you guys is just there. I'm wondering what we're going to see in a second when I apply some pressure to this and what becomes visible. So let's do that now. Okay, we have the pressure applied. Oh, wow. And that was not visible to the naked eye. That wasn't visible to the microscope either at 1,000 times magnification until we applied some pressure. Look at that thing. So I said it ended around there. I was pretty generous with my markings because I knew we dropped it from 80 centimeters, but I said it was in this region, and we've got a huge failure. Now this is on what looks like potentially the last layer of carbon, but the issue you can see here is it passes through additional layers of carbon. So it's not just a resin fracture, this is a carbon fiber breakage in addition to that, and it propagates over a massive distance, and you have a very good example here of additional fracturing through layers of carbon, which I'll just point at now. So here you see one fracture through the resin. The concerning one is the fact that this goes down here, and that must be through another layer of carbon fiber, and then it continues on here. So this is a major failing again, and would render this at a fraction of its strength. Obviously not safe to ride continuously. This might get you home, but not something that I would be comfortable riding, and not something you should be riding too. Let's move on to the other side of number 4. Here is the other side of number 4. We should see similar. All right, so that's just a chipping of a bit of carbon. I think that's just a result of cutting through. Again, you can't really see, there's a few hints at fractures. I'll show you where I think I see the fracture. So I think I see a fracture just there, turning ever so slightly, and I'm touching it with my metal stick. And then we've got another clear fracture here, and we'll see what we find once we apply some pressure. So obviously there's a chip, paint chip there, so that's what was caused, and that paint chip has gone not just through, it's not a paint chip, it's an actual chip in the carbon layer itself. So that is carbon, and then you've got the paint layer on top of that. So let's apply some pressure and see what we get. Okay, we have a tiny bit of pressure, consistent. Okay, this is obviously extremely bad. I don't even need to point it out. It's all there, it's all visible. It's multiple fractures through the depth of the entire material, and obviously not safe. That's not going to support a lot of load. Again, you're only a few bumps away, and this is going to continue to expand with use. It's interestingly not possible to see it from the inside of the tube either. And again, almost all of these were not visible without some additional pressure applied. So again, this sort of pressure will be applied when you're going over bumps and putting your frame under load. That's directly through layers of carbon fiber. Quite concerning. And again, I would deem this failure of the material. Let's move to number 5, the bonus smash test. We have number 5 here. So this is the first half of the cross-section we created. I didn't bother marking it out because we know that based on how bad number 3, 4 are, number 5 is going to be quite a disaster zone. Interestingly, the paintwork itself doesn't look so bad. It looks very minor. Maybe just a small paint chip, but we know we're about to expose a whole lot more. So straight to the microscope. And here we have number 5. Now that didn't take long. Wow. Looking under the microscope, number 5 is definitely the most severe case that we've seen without even needing to apply pressure. We'll apply pressure just for wow. So you can see that it was probably impacted around here, and then to the left is massive amounts of fracturing directly in the matrix and through the carbon fiber layers, and then to the right, likewise, a huge amount of fracturing. Now let's apply some pressure. We'll apply the pressure right here in the middle part to simulate what the hammer did in terms of providing the force. So we're going to push down here. Okay, that's enough pressure. I can, wow, okay. So this just exposes how extreme the damage can be. And you can almost see into its deepest inner thoughts right here. You've definitely got, this is a really good example of a carbon layer being fully separated. So you can see this layer here, that is a layer of carbon. And then this black layer here, you can see that's another layer of resin. And then here there's obviously a carbon layer that's been completely torn through or ripped or cracked. And then there's another layer of carbon beneath this. So the resin layers have been completely delaminated. The carbon has been cracked directly through, and then you've got multiple fracture spreads throughout the material. So again, this is a great example of when the compression forces have nowhere else to go, so they will come through and propagate down through additional layers. And that's where you had a huge amount of the force. So the hammer caused an incredible amount of damage. Let's move around to the other side. So this is where the actual impact would have been with the flat side of the hammer, but then all that bending and wrinkling has resulted in this crushing and fracturing of the material. So again, obviously this is not okay to ride. This will continue to propagate and spread throughout the material over time if you were to continue using it. This is ultra conclusive in terms of, does ultrasound work? Yes. Can it detect small fractures? Yes. We got down to 1 millimeter as we saw earlier with number 1. Can it detect stuff that's not visible on the top? Yes. Can it detect things that are not visible internally? Yes. This technology is perfect for the application of carbon fiber bike testing. Thanks very much for watching, everybody. The conclusion today is very clear. Even from 20 centimeters, you can get, as we've seen, very minor fractures within the carbon fiber structure itself. Something that is still relatively okay to ride on, but something we'd have to monitor over time. And of course, as we've seen, everything from there on being 40 centimeters, 60 and 80 centimeters, especially you see carnage, fractures that cross through between matrix layers, so that's through the layers of carbon fiber, and all sorts of depth as well, from the absolute surface all the way through to the other side of the material. It's been a very eye-opening experience, and I can't say thanks enough for watching. If you have any questions or thoughts or suggestions for what we can do next, please drop those in the comments. I'm excited to explore some new videos with you guys too. Until then, have a great day. Bye.